Okay, so let's start with the question that Abhay had asked in the last class regarding what happens if you have a complex impedance, in the sense that I think question was all this reflection match is not the same as power match, right? So power match is, by definition, power match is the load should be a complex conjugate of the source. Load impedance should be a complex conjugate of the source. But if you want to have a reflection match, then load should be exactly equal to the source, right? So essentially, in both the cases, the treatment is identical, but the results are not, because when we say that I have a load ZL and I have to invoke a complex conjugate match, and which essentially means that the source is also not real. It has a complex part. Then only this complex conjugate matching is different from reflection matching, right? So which essentially means that this is also, it has a complex part, and maybe you have a transmission line and all, and you are connecting these two, and then you do your calculations, right? So in this case, if ZL is equal to ZS, then gamma is equal to 0, and you have reflection match. Okay. And in that case, you go ahead and do your analysis just the way we did. But if let's say, if ZL is equal to ZS star, then clearly gamma is not equal to 0. In fact, I mean, we can figure out what this will be. So gamma is ZL minus ZS by ZS, which is equal to ZS conjugate minus ZS by which is nothing but negative of J, the reactance, divided by R source, where I am essentially saying that ZS is equal to RS plus JX. Okay, so you will have a gamma which is obviously not equal to 0, which essentially means that there will be reflection, right? So that's not a problem. I mean, well, I shouldn't say not a problem. Whether it's a problem or not, that depends on what you are trying to achieve, right? So if I simply give you an example of this, so let's say I have a source which has the source impedance includes this omega L, j omega L. So if you have to do a complex conjugate match for maximum power transfer, then you will have to have this to be, if I say Jx, this has to be equal to minus Jx, which means it has to be a capacitor, and you need to have an Rs here, right? So this is a power match. But clearly, this is not a reflection match, right? So which essentially means that so when you are trying to drive maximum power, derive maximum power out of a source which has an imaginary impedance, right? Which has a phase shifted impedance, then you will have to either live with a reflection, or if you say that I don't want reflection, then you will not be able to transfer maximum power. That's the consequence of it, right? But fortunately, in most real systems, it's not a case, because I mean, the antenna is in general can be modeled as mostly a real impedance. There will be some remnant of imaginary part, but that's okay. Right? So this is a power match, but not a reflection match. Okay. So you can do the same analysis here also. Let's say I assume this is the plane where I am trying to find out the reflection coefficient. So clearly in this case, your reflection coefficient is gamma is minus Jx over Rs. And then your forward going wave, V plus, as usual, will be Vi by 2, right? Because while doing a forward going wave, we are assuming that there is probably a transmission line which has the same characteristic impedance as that of the source, and you don't when the forward going wave moves through, it doesn't know whether it is terminated or not terminated with its characteristic impedance. So it is going to go through, right? So, and then and if there is some termination, which is not exactly equal to Z0, then there will be a reflection, and this reflection is essentially taken care by the reflection coefficient. So you will have a V minus, which will be equal to gamma Vi by 2, right? And naturally, if I say V1, and in this case, I'm assuming the delay of this transmission line is close to 0. Otherwise, you are going to have that extra stuff, right? So assume delay to 0 approximately. So your V1 will be, as usual, Vi by 2, 1 plus gamma, which in this case is 1 minus Jx by Rs. And you do the math in the classical way, you will get the same result, right? Okay. Does that answer your question? The negative effects are usual, the same thing, right? I mean, if you have a long line and there is a reflection, and let's say you are sending multiple symbols, right? And you do not have match, which means there can be interference between the symbol that you are sending now and the next symbol. Pardon?
Main issue is the delay of the transmission.
Yes, main issue is the delay of the transmission. If you don't have a delay, not an issue at all. Everything is lumped and no intersymbol interference, no problem. In fact, S parameters itself is not required if you do not have a delay. Okay, fine. Any other questions? So we were discussing about distortion in the previous lecture, and the part that we were discussing at that time was what happens if you have two tones which are applied simultaneously to your RF system, right? So the background was, let's say you have some amplifier which gives some gain. And by definition of narrowband RF systems, we know that there will be some matching network somewhere and some filtering somewhere, because ultimately we want a narrowband match. We want a narrowband transmission. Out of band is bad, and narrowband, in band is good. So essentially, you have, if I say the transfer function from this point to this point is H, so where is A naught, right? A naught is a DC gain. So if I say that this amplifier has a profile like this, right? So then there is a problem with this profile. Then there is a problem with this profile if this comes directly at the front end, directly after the antenna. What is the problem? The problem is maybe your signal of your band of interest is somewhere here, if not, and around if not. This is where you want to be. Everywhere else is out of band, which means somebody else is transmitting there. Okay. And which means there can be very high, there can be jammer signals, there can be blocker signals of very high amplitude and all. This we have discussed in detail in one of the, at the beginning of the course. So the crux of the matter is that just because you can design a wideband amplifier, right? It's not necessarily a good thing to put it right after the antenna before any filtering. Okay. So which essentially means that there is a filtering associated with when you design something, there is a SAW filter, then there is probably a band pass filter, a matching network, which will give some filtering and so on and so forth. So essentially you end up with an H which looks like this, which probably has a peak around your center frequency F naught, and it rolls off after some bandwidth around F naught. Okay. So now the question that was in front of us was, if this is our system, and I know that this amplifier, I mean, if I have a broadband amplifier, I can make it narrowband by simply putting a matching network here. A matching network there. And these matching networks, let's say, have these narrowband characteristics. Okay. So now let's assume that I have a sinusoid here, Vp sine omega naught t. So, and we understand from our treatment of amplifiers in other courses, these amplifiers are made up of obviously transistors which are nonlinear and so forth, which means that I can express its characteristics as V naught to be is equal to, so V naught to be equal to some VDC plus some A1 V in, where V in is the incremental input voltage, plus A2 V in squared, plus A3 V in cube, and so forth, right? And if it's a weakly nonlinear system, I'm limiting my Taylor series expansion to the third order term. And if that is the case, and if I now evaluate the effect of this system when the input is Vp sine omega naught t, so clearly this term is going to give me an output at 0 frequency, right? So omega VDC will give you at 0. The second term is going to give you a output at omega naught. The third term is going to give you an output at DC and 2 omega naught. And the last term is going to give you outputs at omega naught and 3 omega naught, right? So if that is the case, and let's assume that this delta omega, which is around F naught, is much, much less than omega naught, right? Or in other words, if I take an example, let's say F naught is 1 gigahertz, and this del F is, let's say, 10 megahertz, right? So here F naught is at 10 at 1 gig. This is at 0, and this is at 2 gig. This is at 1 gig. This is at 3 gig. And this is at 0, obviously. So one might be tempted to think that, so what if I have distortion in the amplifier? This 2 gig is out of band, 3 gig is out of band. And the bandpass nature of the matching network or the amplifier is going to filter it out, which is a fair assumption, which is a fair statement to make. But the thing that you should be, but the thing that you should be aware of is you never send a single tone. You send multiple tones, right? Or even if you think of an aperiodic signal, right? So aperiodic signal you can think of as a bunch of tones put together, which are infinitesimally closely spaced, right? So which essentially means that this is not a realistic scenario to evaluate distortion. A more realistic scenario will be to apply multiple tones and then see what happens, right? So that's what we were doing at the end of the last class, where we said, let's apply 2 tones instead of doing multiple tones at a time. Let's apply 2 tones, where the assumption is, so I'm just now magnifying this band. So let's say this is the band. If not, let's say I applied 1 tone here and another tone here, right? So this is F naught minus delta F. This is F naught plus delta F, right? Where delta F is less than 3 dB. But this is a 3 dB. You can assume this to be twice f 3 dB. Okay, so then what happens? So then we saw that there are what happens is you go back to your trigonometric identities, and then obviously so this expansion leads to outputs at f naught minus delta f and f naught plus delta f. This expansion will lead to what? You are going to get so we can write it out fully. So V in squared will lead to Vp sine omega 1t, where I am saying this 2 pi f naught minus delta f to be omega 1 plus Vp sine omega 2t whole squared, which essentially means that I get Vp squared sine squared omega 1t plus Vp squared sine squared omega 2t plus 2 Vp squared sine omega 1t sine omega 2t. So this, if I expand, the first term, if I expand, creates 0 and 2 omega 1. Second term, if I expand, creates 0 and 2 omega 2. So note that both 0 and 2 omega 1 or 2 omega 2 are way out of band, right? So not a problem. This term, if I expand, is going to create omega 1 minus omega 2 and omega 1 plus omega 2. Again, both are way out of band, right? Because omega 1 and omega 2 are close by. So this essentially gives me twice of delta omega. And this is approximately twice of omega naught, right? Because the assumption was both the inputs were very closely spaced, right? So again, looks like this is also not a problem, right? So before I move on, if I say it's not a problem, it's not strictly true, it's not a problem. So clearly there is an issue with some things falling back on DC, right? And the amount of signal that falls back on DC is also proportional to VP. So the larger the VP, it looks like it adds to the DC offset. You set the bias with some value, right? When you have to bias an amplifier, you have to give some DC bias. You set it as some DC bias, and you apply a sinusoidal input. But this, because of the distortion, you will see that at the output side of the amplifier, the DC bias that you intended to set has deviated. And that deviation can be quite large, given that this VP is typically may not be in your control at times. Okay, so that can be an issue. That is often referred to as second harmonic DC shift in RF parlance. But for now, that is not the major thing, right? The major thing comes next. The major thing is that happens when I have the cubic nonlinearity, and this is where we stopped in the previous lecture. So if we have V in cube, so then we essentially get Vp sine omega 1t plus Vp sine omega 2t whole cube. So the terms that you get are, naturally you get omega 1. So basically, so you get like cubics of each of the term, then 3 times Vp sine square omega 1, sine omega 2, and 3 times sine omega 1, sine square omega 2, right? So essentially the terms that you get are the usual ones, which are 3 omega 1 and omega 1, then 3 omega 2 and omega 2, right? And then you get something which are 3 omega 1, sorry, 2 omega 1 minus omega 2. You get plus minus, in this case it will be minus. omega 2, and then you get 2 omega 2 minus omega 1. You will get some more terms, but again, they will be out of band, so you don't have to bother about too much of that. The thing that that should be bothersome is all of these have the coefficient of Vp cube, and also it has the coefficient of A3, right? Because everything gets multiplied by A3 times this. A3 times whatever you have here, times, obviously, this is a sine of this 3 omega 1 t and sine and cosine and so on. So the problematic terms clearly are, one is, you see that something is falling back on omega 1, right? You expected only the fundamental to contribute to omega 1, but looks like because of a distortion, something is falling back on omega 1. This may or may not be an issue depending upon how big your signal is. We'll talk about how to characterize this part. But the key thing to note here is that if you look at these terms, 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1, what do you observe there? So if you have, if I redraw the spectrum, if not, then applying, this is omega 1, which is at f naught minus delta f, and this is omega 2, that is f naught plus delta f. So 2 omega 1 minus omega 2 is essentially how much? Twice f1 minus f2, if I write. 1 minus f2 is twice of f naught minus twice delta f minus f naught plus delta f, which means this is f naught minus 3 delta f, right? So you are going to get a tone at here, which is 3 delta f away from the signal, 3 delta f away from f naught, or 2 delta f away from the signal that you have applied. Similarly, you are going to get another tone here on the other side. Okay. So these tones are, now this is a bigger problem because you are not expecting any tones there, right? You applied a pristine sinusoid at f naught, at f1 and f2, but you are getting tones very close by, and this can be misconstrued as another signal that is coming in, right? So there is no signal that is there, but because of the distortion, you might be tempted to think that there is another signal that is coming in. So that clearly is not a good thing, right? So there is a way, and by the way, better the amplifier, lower will be this red delta, or the higher will be the difference between the heights of the intended signal and the unintended signal, right? And what's the amplifier, smaller will be that difference for the same amount of input amplitude, right? Note that if the input amplitude increases by 1 dB, right? If Vp increases by 1 dB, how much will this increase by? Let's say Vp increases by 1 dB, how much will the blue delta increase by? Yeah, gain is embedded in this case also, right? So let's say gain is there, right? So let's say the linear gain is, let's say 10, right? So input is 1 millivolt, output is 10 millivolt. Input increases by 1 dB, output will increase by how much? If input increases by 10%, output will increase by 10%, right? Percent is nothing but dB expressed in linear scale, right? So input increases by 1 dB, output will increase by 1 dB, right? So this guy will increase by 1 dB per dB, right? So this expression means that the output increases by 1 dB, for every 1 dB increase of input, right? So this is output change, and this is input change. But what about the red guys? If input changes by 1 dB, what will be the rate of change of the red tone? It will be 3 dB, right? Because it goes by Vp cube, right? So it will go by 3 dB. So this will be 3 dB per dB. So clearly you see that this if you're not careful, this red tone can catch up with the blue tone for reasonably high amplitude of the input, right? So that's why anything that is connected to the front end, it becomes imperative to characterize it for good amount of linearity, right? When I say good amount of linearity, we'll define what I mean by good amount of linearity. But essentially, you get the idea that why it is important. Okay. Yes. 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 I'll come to that. So as he is pointing out, say here, I have very tactfully neglected the effect of this guy that has come down on the fundamental and was contributing to the fundamental also, right? So which means the output should not go by 1 dB per dB. It should be different. It should be either larger or smaller, depending upon the sign of whatever has been holding back, right? So that's what we'll see next. So what is the contribution of this omega? What is the contribution of this fallback thing, right? So we see that for this, if I just simply take the first order, the single term, that is, you have A3V in cube, which creates, if I take only one sinusoid, for example, then it creates A3 Vp cube sine cube omega 1t, which means this gives A3 Vp cube by 4, 3 sine omega 1t minus sine 3 omega 1t. Right? So, and this guy adds up to my fundamental. My fundamental was A1 V in. So fundamental was A1 V in, so it is A1 Vp sine omega 1t. Right? So therefore, at omega 1, you tend to get A1 Vp plus A3 Vp cube by 4 sine omega 1t. Right? Right. 3 by 4. Right. So now it all boils down to the sign of A3. Right? So in the sense that if sign of A1 and A3 are the same, then you are going to get an extra, I mean, in the sense that you are not going to get 1 dB per dB, you are going to get more than 1 dB per dB increase. But if A3 and A1 have opposite sign, then you are going to get lesser than 1 dB per dB increase, right? And as it turns out, in MOS amplifiers, which are biased in weakly inverted or even in saturation, A3 and A1 are opposite sign. So that's why if you plot P in dBm and P out in dBm at very low amplitude, that is very small Vp, where I can neglect this Vp cube term. So this guy the output will look like, how will it look like in terms of dB? dB plot. If I neglect that Vp cube term, straight line, right? So it will look like a straight line having a slope of 1 dB per dB. But if A3 is of negative sign, No, not decade. I mean, x-axis I'm plotting dBm, y-axis I'm plotting dBm. Right? So it's a dB plot, right? So if A3 is of negative sign, if A3 is of the opposite sign of A1, so clearly this when the second term starts to make its presence felt, right? So then it will not increase by 1 dB per dB. So this guy will go by, it will start going down, right? It will start flattening out. So there is a metric to judge this. So you extrapolate this 1 dB per dB line, and then see at what input power the difference becomes more than 1 dB with respect to ideal. So that input power is called P1 dB. This is basically a definition. So P1 dB is essentially the amount of input power, input referred power, for which you see a gain compression, right? You are seeing this is essentially a gain compression. It should go by 1 dB per dB, but it's not going, it's reducing. So the power level at which you see a gain compression of 1 dB is a metric to understand how linear your amplifier is, right? So clearly, if you want a very linear amplifier, you would expect this P1 dB to be to the right or to the left. To the right, right? So higher and higher P1 dB will be means a good amplifier, right? So when you see research papers, I mean, nobody is going to tell you harmonic distortion, this and that. They are going to tell you this P1 dB is this much, right? From there, you have to interpret whether it's a good number or bad number. So typical P1 dBs for front ends can be anywhere between 0 dBm to 10 dBm to 20 dBm, depends upon applications again, right? So 0 dBm is often an acceptable P1 dB number. But again, you cannot simply quote P1 dB without quoting many other things, but some ballpark numbers that you should be aware of, right? So this is, I should also write this down. So P1 dB is the input power level where the output sees a gain compression of 1 dB. Okay, any questions so far? Fine. So this is as far as looking at the amplifier from the lens of fundamental is concerned. The P1 dB essentially is plotting your fundamental, and you are trying to see at what frequency the output, at what power level the output compresses. By the way, when the output is already starting to compress, the system is already nonlinear. That much we understand, right? Because it is sufficiently nonlinear that it is visible that the gain compression is happening. So the value of P1 dB, when if somebody tells you my P1 dB is 0 dBm, that does not mean that you can apply a input at 0 dBm and still expect the output to be okay. The output is already nonlinear. So which essentially means that you probably will have to apply few dBs below P1 dB level to make sure that your system works, right? Yes, yes. So that's a good question, because sometimes, because it is not very straightforward at times to plot only the fundamental, we tend to plot everything and then see where is this compression. In that case, the assumption is that the other components are not dominant. Sometimes you will see that we plot the total harmonic, I mean, the entire power, not necessarily the first harmonic, and then see where the compression happens. But that's again an assumption. But ideally, it should be the fundamental power. Okay, so completing the thought that if I say that my amplifier has a P1 dB of 0 dBm, that doesn't mean that you apply a 0 dBm input and everything will be fine. There will be no distortion. Obviously, that doesn't mean that that's not the case, because when you say P1 dB, when you define P1 dB, you are already saying that there is enough distortion to reduce the fundamental gain, which means that if you want to work, if you have to make that amplifier work, you have to apply input of maybe a couple of dBs below the P1 dB mark. Okay. So that is a typical thumb rule, but again, how much is dependent upon how much distortion your spec tolerates. Okay. So now another way of characterizing distortion in RF systems is by looking at this term, the strength of this red term, right? So by the way, there is a term associated with this, just like anything else in RF. This is called an intermodulation term. This is called intermodulation, third order intermodulation. Component. Why intermodulation? Because obviously it's mixing between it's basically you have two tones which are getting mixed and then passed through a nonlinearity, which is causing this. So there is an interplay between two tones and hence intermodulation, and often referred to as IM3. IM is intermodulation, 3 refers to as a third order. Okay. If you refer now, sometimes you will see that if you look at papers or textbooks, sometimes you will see it's referred to as input IM3 or output IM3, right? So when we say input IM3, it essentially means that everything is happening at the output, that we understand. But we would just like input referred noise, we would like to understand what is the input referred intermodulation component. So you divide IM3 by the gain, fundamental gain, the number that you get will be input referred IM3. And if we simply say IM3, sometimes it's better to be clear what you are talking about, output or input. So if you are talking about IM3 at the output, you should say OIM3. O refers to output. And if I refer to as input refer, you should say IIM3, right? Okay, fine. So now if I plot this, P out, and if I plot fundamental, then, and this is P in, again in dBm. So we are getting whatever we are getting, I mean, some straight line, and then there is some tapering, right? So this is the fundamental plot. But if I plot on top of this, if I plot this IM3, let's say output referred IM3, if I plot, what should I get? So I am plotting OIM3 also in dBm. Then what should I get? I mean, it should start from somewhere, but what will be the slope? 3 dB per dB, right? And it is expected that it will go something like this. And then something will happen, right? Because I mean, there are so many other tones will come and the slope will not remain 3 dB per dB for really high power. Something is going to happen. So generally what is done is to say that I will plot a couple of points at very low power where I know that the dominant term for this OIM3 is still 3 dB per dB, and I'm going to extrapolate that line. Physical extrapolation, put it in MATLAB, put it in Excel, just extrapolate. So you extrapolate this line. Similarly, you extrapolate the 1 dB per dB line also, because I mean, if you are a very large power, then you can get this gain compression. But if I simply extrapolate this 1 dB per dB line, these two hypothetical extrapolated lines are going to meet somewhere, right? So let's say they meet at this point. Some value of the extrapolated, I mean, some extrapolated value of P in at some extrapolated value of P in, these two lines are going to meet. Now, does this intercept give any information as to how linear your network is? In other words, what I'm asking is that, let's say I have two systems where I say that this point is at 10 dBm. I have another system where that point is at 20 dBm. With regards to the third order distortion, can you make a comment of which system is more linear? 20 dBm, right? Because clearly, so second one probably has an intercept which meets somewhere here. right? So this also gives you an idea of how linear your circuit is or network is. So this intercept is called, at the input referred, is called IIP3, which essentially means that this is the input referred third order intercept, where IM3, extrapolated IM3 becomes equal to the extrapolated fundamental fundamental power, right? So that by definition, this is that extrapolated value of P in for which the extrapolated IM3 is equal to extrapolated fundamental. The extrapolated is the key word here, because again, these values that you will get IIP3, whatever value of IIP3 you get, it doesn't mean that you can apply an input at that power and expect the system to work, because clearly it probably will be at much higher power than even P1 dB. So, but just like anything else, you need to understand in a short way that whether the system is linear or not, how linear it is when you compare two systems. So when you are talking about third order distortion, you basically then say that if you have two systems for which you have certain IIP3 numbers, clearly the one with higher IIP3 number will be more linear than the one which has a lower IIP3 number. Okay, and clearly you see that these two, P1 dB and IIP3, the origin of these two are the same, right? It's coming because of the third order distortion component. So these two must be related, right? So I will leave it up to you to find out the relation. It's basically a bunch of algebra. You expand both terms and equate. So you will see that your IIP3 is approximately equal to P1 dB plus 10 dB. Do it yourself, okay? So this is an easy hack to remember. Let's say you have a certain network, weakly nonlinear network, right? That's the important thing. You have neglected all the other distortions. You have neglected fifth order, fourth order, all those distortions. So if it's a weakly nonlinear network, then you simulate and you find out P1 dB, and you simulate, you find out IIP3, and you see the number difference is probably 20 dB, and something is wrong in your setup. Okay, so that's an easy way to figure out whether you are in the ballpark range or not, right? But it will never be exactly 10 dB. It's supposed to be 9.6 dB, but it will never be exact, but it will be in the ballpark range. You should be able to appreciate whether that is correct or not. Okay. Okay. Any other questions? Yes.
Usually depend on the ratio of the amplifier constant A1 and A3.
Correct. Yes, they will. Obviously, right? Both are ratios, because I am taking the intercept in both cases. So obviously they are ratios, but the ratios will also depend upon, I mean, they will definitely be depending upon A3 and A1, but how they depend are basically the details of algebra. I leave it up to you. Okay. Yes.
So what can happen is that
What can happen means? Okay, good question. So his question is, I said that it's an extrapolated line. The red line is an extrapolated line. But what can happen if I do not extrapolate and I let it go in actual scenario? So clearly in this formulation, there will not, it will go as a 3 dB per dB line, because we have limited our expansion to A3V in Q. But let's say I have A3V, A5V into the power 5. Then you are going to get one term which is squared times cubed. So they will fall back on fundamental, or even the one, I mean, omega 1 and then omega 2 to power 4. Right? So the 4 minus 1 will be 3. It will fall back. So as you keep on increasing the amplitude, those higher order intermodulation terms will fall back on third. and this will not become straight, it will wiggle. Sometimes you will see that when you do your inline design simulation, you will see that that's a good observation. You will see that this line, if you keep extrapolating, it will sometimes expand, sometimes compress, it will do all sorts of things. And that is, I mean, a priori, it is very difficult to understand why. So you'll have to extract each of those Taylor series terms to figure out how it is going to behave around that operating point. Yes, yes. It's basically the biasing, right? The signs of the coefficient depends on where you bias. The Taylor series is totally based on the derivative of the curves around the operating point. An operating point is where you bias. You plot IDVGS, right? You plot IDVGS, you take your differential around the operating point, you are going to get bunch of terms. From the bunch of terms, you will know that whether it's going to expand or compress based on what type of, if that term becomes dominant or not. And that will give you the idea.
We are not we are extrapolating because we know that at higher power, it is not just IM3, it is like IM5.
Yes, yes, yes. So similarly, if you are looking for terribly linear circuits, right, then IM5 also becomes important, but very rarely such circuits are needed. I mean, there are other issues that come in before you go to IM5. The part that I haven't really mentioned here is also that, okay, so the question that should have come, I was anticipating maybe somebody will ask, that why are we only interested in third order? Why not second order? Right? Because second order seems to be also, it's affecting the DC part, right? So, so I kind of bypass that, saying that that's not a main issue. One of the reasons that may not be a big issue is if you are using a differential circuit. If you use the fully differential circuit, and 613 probably it has been covered, I'm not sure, right? Okay. If you use fully differential circuit, then the second order distortion gets suppressed, right? They get cancelled. So they are not dominant anymore. If there is a mismatch, then sure, there will be some. But in general, they are not dominant, so you can neglect them. But having said that, there is an issue also that normally antennas are single-ended. So when antennas are single-ended, which means the LNA that is attached to it is also single-ended. So in that case, in case of LNA, you need not always neglect the second harmonic term, and second harmonic causes, similarly, just like you have P1 IIP3, second harmonic will give rise to IIP2, right? So, but that is not part of the discussion right now, so I will leave it out. If you are interested, you can look it. Okay, so this is as far as the definitions are concerned, right? But it's not a definition or an analysis course, it's a design course. So which essentially means that we need to understand how, what are the design levers that I have to make a circuit linear, right? So let's start with the good old common source amplifier. And you can tell me what are the things that you know that we can make, that we can use to make a common source amplifier more linear. Right? You started off with something, you got some linearity number. I want to make it more linear, right? So what can I do? So I don't even need to draw the load. So let's say I have VGS, we have VDS. So clearly, if you do only square law model, you will be tempted to think that there is no third order distortion, right? It's only square law, right? But in real MOSFETs, it's never square law. It's in fact quite complicated. So if you just simply plot VGS, and do a Taylor series fit, or even do a double differential, triple differential, keep differentiating, you are going to see that you're never getting a zero, right? So if you never get a zero, which means all the derivatives exist, which means it's definitely not a square law. So you ran your circuit simulator and you found that this is, you got some value of A3, A1, and so on, right? So you got, so in this case, if I say your IDS will be some IDC plus the first order is essentially GM times VGS. Let's say the second order is G2 times VGS squared. the third order is G3 times VGSS cube plus dot dot dot, and I'm neglecting them. By the way, I'm also assuming that this is for a certain VDS. The VDS is not changing. If VDS is changing, then this Taylor series should also have VDS terms, right? So this is constant VDS. So which means that I have some battery connected here. Okay. So now tell me, what are the ways you know that I can make this network more linear? Pardon? Make VGS more, right? So if I make VGS more, even from the make VGS small, okay. Okay, you mean incremental VGS small. But let's say I do not want to make incremental VGS small because that comes from the input, right? So then what? So by the way, when you say make VGS small, in this case, clearly, if I make VGS small, it is going to smaller. It is going to lead to better distortion performance, no doubt. But if I do not want to make VGS small. When you say VGS small, which means what? Small with respect to something, right? With respect to what? At the edge of saturation. But if I just look at this this expansion, and I say that I want I want the GM-VGS term to be dominant, right? Then I'm naturally saying that GM-VGS should be higher than G2-VGS squared plus G3-VGS cube. Correct? Which essentially means that I am saying that for a certain VGS, I do not want to change VGS. So what I'm essentially saying is that GM-VGS should be much greater than G2-VGS squared plus G3-VGS cube, which means for a same VGS, or let's say I take only one at a time, right? So let's say this is the one that is going to dominate first, and then the subsequent ones, which essentially means that your VGS should be much less than GM over G2. So if I do not want to change VGS, what should I reduce or should I increase? Yeah, I have to, and for a fixed GM, I have to reduce G2, right? So what does G2 depend on? So if I do a square law, if I simply do a square law model, so what will G2 depend on? So let's do that, right? So, so your IDS is mu n Cox W by L VGS minus VT whole square. So you are applying an incremental VGS, so you get IDS naught plus delta IDS to be equal to the main one plus delta VGS squared plus twice V over drive times VGS. So which essentially means that your delta IDS is GM times VGS plus this half mu n Cox W by L delta VGS squared, right? So which is your G2 here? G2 is this. And what is GM over G2? GM over G2, GM is, yeah, right? So basically ratio of these two, right? So 2 times mu n Cox W by L times V over L. Or the other way around. This is GM and this, fine. Correct? So if you want this to be the dominant one, then clearly you will have to bias it with higher and higher overdrive. Right, sorry. Thank you. That's what I was thinking, something is wrong here. Okay, so clearly, as a designer, this directly tells you that if you have to increase linearity, at least if I limit myself to second order distortion, right, from the simplistic model that I have, it seems like increasing the quiescent overdrive is the way to go. And that should make sense. Why? Because ultimately what is happening? What is the root cause of distortion in the current? The root cause of distortion is you have some bias, right? So let's say this is your threshold voltage, right? This is threshold voltage. And you have biased at some VGS naught. So this is your overdrive. And when you apply a sinusoid on top of this, you are eating into that overdrive, right? So your effective overdrive is changing from this high value to a low value as a signal proceeds in time, right? And because your device is a nonlinear function of the overdrive, more the fraction of this overdrive you are eating out, more will be the distortion, right? So essentially, in order to reduce your distortion, all you have to do is to reduce this fraction of overdrive that you are eating away, right? And this is true for, even though the square law model doesn't predict what's going to happen for third order, this is true for any order distortion, right? You bias with higher overdrive, maximum overdrive, you are going to get better and better distortion performance. But naturally, you see there is other problem. If you bias it with very large overdrive, the VDS nonlinearity will start coming into picture. So there is a balancing act. Okay. Yeah, fine. So we'll stop here. And in the next class, we'll start off and see what are the other handles that we have. And then we'll start off with a LNA design example. Okay. Okay.
Higher operating. We want to add